Hello, I'm Dr. Bean, apparently. HowToFly created this deep fake version of me to explain how AI can create high-quality images out of simple text prompts with the help of something which is known as diffusion models. In today's presentation, I will start by providing you a quick overview of my favorite image generation models and tools out there. Then I will provide you with a high-level technical explanation how these AI diffusion models are capable of creating images out of thin air with just a text as input. After that, I will share some practical use cases of diffusion models, including SORA for video generation and AlphaFold 3 for protein structure prediction. So now that you know what we will be covering today, let's get started by providing you a quick overview of my favorite image generation models and tools. In my opinion, DALL-E is very good in creating visuals which include logos and text. So if I want to mock up some of my product ideas, like a bean-infused ice cream, a bean-based crisp, or a logo for the Mr. Bean's coffee shop, I would go to ChatGPT and ask DALL-E for a design. Midjourney, on the other hand, is very capable of creating high-quality, more cinematic visuals with a lot of realism. You can even feed it visuals that it can use as style references or face references to use during the generation process. This is me, for example, as a character in a Guy Ritchie movie. Adobe Firefly is great for quick Photoshop edits, as it's integrated in Photoshop. For example, I can ask it to change the color of my tie or remove something from the background. Finally, there's Stable Diffusion. Stable Diffusion is an open source text-to-image model. This means the code can be accessed and altered by anyone, and it can be run locally on sufficiently powerful hardware. When running Stable Diffusion locally, users can interact with the model through user-friendly interfaces like Automatic 1111 or Comfy UI. While these interfaces have a higher learning curve compared to the interfaces of commercial models like DALL-E and Midjourney, they offer a lot of versatility in visualizing ideas and in fine-tuning the Stable Diffusion model to your specific needs, such as learning your personal face or your organization's visual brand identity. For those without powerful hardware, GPU power can be rented in the cloud through providers like Run Diffusion, or they can use and fine-tune the Stable Diffusion models through a commercial, non-local interface, like, for example, Leonardo.ai. Going into all the capabilities of all these tools goes beyond the scope of this presentation, but I'll include some great YouTube tutorials for each of these tools in the description section. I hope this overview of my favorite models and tools gave you a bit of insight into how you can experiment with AI image generation yourself. Now we have arrived at the second part of my presentation, where I will give you a high-level theoretical explanation of how diffusion models actually work. And it's quite fascinating and not even that complicated, so bear with me. Let's say you provide the following text input to a diffusion model like Midjourney. Create a visual of a cat on a surfboard holding the Mona Lisa in Pixar cartoon style. After doing this, the following sophisticated process unfolds. First, the diffusion model uses a large language model to transform your text input into a context-aware embedding. If you don't know what a context-aware embedding is, make sure to check out our video where Ryan Gosling explains how large language models or LLMs work. But for now, just think of an embedding as a numerical representation of the input text, which captures the exact meaning of the text in a format that computers can understand. This context-aware embedding is then paired with an image containing completely random noise. This random noise image, also known as the seed, doesn't contain any recognizable patterns or features. It's purely random. Together, they serve as the starting point for the diffusion process. Now the diffusion model undertakes approximately 1,000 iterative steps to denoise this image. In each step, the model slightly manipulates the image to gradually transform the random noise image towards one that matches the description provided. This iterative process is the core of how the model turns abstract noise into a coherent image. In every step, the model takes into account the following information: the embedding of the input prompt, the time step, and the current image state. This data is then used to predict the next, less noisy image state, which matches more closely the text input prompt. Now you can ask yourself, how does the diffusion model manipulate the image to make it less noisy and closer to an image that depicts the input prompt? To better understand this, it's crucial to be aware that the model does not draw as a human artist. Instead, it works by adjusting the pixel values of a digital image across numerous iterations. Let's deep dive into what we mean with this. First of all, remember that a digital image is essentially just a grid of pixels, which are essentially tiny, square-shaped, colored dots. The arrangement and color of these pixels determine the final visual appearance of the image. Even simple images at a low resolution, such as this 18 by 18 pixels grid, can already visualize, for example, Super Mario in a distinctive way. Of course, the more pixels you have in the grid, the higher the resolution of the image and the more details you can see. But for simplicity reasons, we'll stick to this very low resolution image of Mario to make our explanation of how diffusion models work more tangible and easier to understand. But be aware, exactly the same principles are used to work with higher resolution images. Let's now look at how the diffusion model can manipulate random noise images and turn them into a structured image, like for example Mario. First, you need to know that the diffusion model does not manipulate the image directly. It manipulates a numerical representation of the image known as a tensor. Before you can understand how an image can be represented by a group of numbers, you have to understand color codes, like for example RGB, which stands for red, green, and blue. Every visible color can be represented by a mix of red, green, and blue. An RGB code is exactly doing this. With three numbers between 0 and 255, it indicates respectively how much red, green, and blue is in the color. This color, for example, has the following RGB code. Now that we understand RGB codes, how do we use these RGB codes to make a numerical representation of the image so that it can be processed and manipulated by the diffusion model? Very simple, actually. For every pixel in the image, an RGB code is created to represent its color. For example, the first pixel is white, so the first value in the tensor is 3 times 255, which is the RGB code for white. The second pixel is again white, so again the same code. I'm not going to go over all 324 pixels, as I assume you get the picture. So what actually happens in a diffusion model? How does the model go from the random noise image and its corresponding tensor to the final tensor containing the information of the Mario image. It does this by predicting the noise difference between the starter tensor and the final desired output tensor, and subtracts that difference from the starting tensor. So it looks at the random noisy starter tensor. It looks at the input prompt with its context-aware embedding, and based on that information, it predicts the noise that needs to be removed to arrive at an image tensor that showcases Super Mario with a red hat, blue pants, and brown shoes. It then subtracts that predicted noise tensor from the starting tensor to arrive at the final tensor, which corresponds with the image of Mario. It's important to be aware that it doesn't do this in one step, as I've shown in the example, but it does this denoising process over approximately 1,000 steps. This iterative process makes the process more stable and robust. Here's what the process could look like for our 18 by 18 pixel Mario example. And of course, this was just an example with a low resolution image just to showcase you how the pixels are being manipulated to shape the image. Of course, the same can be done with high resolution images such as a 1000 by 1000 pixel image. It only requires more calculation power, as much more pixels should be manipulated. Now you may ask, how does our model know which noise it needs to remove to go from a noisy starter image to the desired output image? In order to better understand that, we need to look at how the model was trained. So let's have a closer look at the training process of a diffusion model. During its training, the diffusion model learns by processing a large data set containing millions of images, each paired with a caption describing the image. For every training step, it picks an image from the training set, together with its description, and starts processing it. As a simple example, let's say our low-resolution Super Mario image is part of the training set and is chosen together with its image description. First, the model gradually adds noise to the image until the image is fully diffused to completely random noise. This process of diffusing the image is called forward diffusion. Then, once the image is fully diffused, it tries to reverse the diffusion process by only taking into account the random noise image and the image description. To measure how well it's doing, it's comparing its predicted images with the actual images of the forward diffusion process. The closer the predicted images are to the actual images, the better it's doing. Based on its performance, it adapts the model parameters in the hope it will now do better in predicting the images. This process gets repeated for all images in the training data set. So a lot of opportunities for the model to fine-tune its parameters and improving its capabilities to turn random noise images and text into an image which depicts the text description. Once it's trained, it only uses this backwards diffusion process to turn image descriptions into beautiful images. As I was intrigued by this training process, I tried to mimic it myself in order to become a better artist. Here's some footage of me experimenting with the diffusion training process.
Oh, God! Oh, Jesus, God! Oh, Mary, Mother of Jesus, Jesus of Nazareth!
As you can see, my friend wasn't really impressed by the result, but I'm sure if I continue practicing and apply this process on millions of paintings, I will get better at it. This brings us at the final part of my presentation, where we will have a quick look at a couple of practical use cases where the power of diffusion models can be tremendously useful. Use case 1. Quickly create a personalized illustrated storybook, which you can use to explain to your kids, for example, how diffusion models work. Use case 2. Quickly try new hairstyles like bald, curly, slick, blonde, or with a beautiful moustache. Use case 3. Try on a new clothing style to match with my new look, like something pink and dashy, a Hawaiian shirt, or a hoodie perhaps. Use case 4. Quickly visualize your creative product ideas, like my own line of beanies. You can combine it with use case 3 to try them on virtually. Use case 5. Use an image generator to quickly generate a fancy logo for my beanie brand. Use case 6. Quickly get inspiration for my Mr. Beanie online webshop. Use case 7, video generation, as a video is essentially a sequence of still images or frames, rapidly displayed one after the other. Diffusion models are also being applied to video generation tools like OpenAI's SORA and Google's VO. However, unlike image diffusion models that operate on single frames, these video models diffuse and generate entire sequences of frames together. The key innovation is modeling not just individual frames, but the complex dynamics and interactions across multiple frames to ensure temporal consistency and realistic depiction of motion in time and space. While still limited in accurately modeling complex physics, SORA and VO represent a significant step towards artificial general intelligence that can understand and interact with the physical world in motion. We plan to cover the technical details of this process in an upcoming dedicated video, so make sure to subscribe. A final groundbreaking use case of diffusion models is molecule structure prediction with Google DeepMind's AlphaFold 3. Historically, determining, for example, a protein's 3D structure was an extremely difficult process, often taking years or even an entire PhD project for a single unknown protein. Now, by simply inputting the amino acid sequence, it can generate highly accurate structural models in a matter of hours or days, depending on the protein size. And it doesn't stop there. AlphaFold 3 can predict and visualize not just the structure of individual proteins, but also their complexes with nucleic acids, small molecule ligands, ions, and various chemical modifications, providing a more complete structural view of biological systems. This capability holds immense potential for accelerating drug discovery, unraveling biological mechanisms, and enabling scientific breakthroughs across medicine, biotechnology, and environmental applications. These are just a couple of my favorite use cases. If you can think of others, don't hesitate to share them. This concludes my presentation for today. If you liked this presentation, don't hesitate to give me a thumbs up. If you want to learn more about generative AI, then make sure to subscribe to HowToFly's channel. Thank you for your time. Stay curious and keep exploring.